this computer. All right, we're recording. Welcome to the Zeke Show, where I interview professionals and learn more about the work that they're doing. Also, this is the first time it's ever been called the Zeke Show. Today I have Ian Shoemaker, who is a physicist who lives in the backwoods of Virginia, an old friend from high school joining me. Welcome, Ian.
Thanks, Zeke. Yeah, I'm very happy to be here.
I like that you have
The particular backwoods are Blacksburg, by the way.
Blacksburg. Okay.
Blacksburg, Virginia. Yeah.
So you're insulated from all of the DC.
Yeah. It's sort of in a valley surrounded by mountains. It's pretty close to the Appalachian Trail. So
Yeah.
very nice place to be around.
And is there a particular reason for physicists to find themselves in that neck of the woods?
Well, it's sort of I guess it's an issue of gravitational attraction, Sometime many years ago, a couple of physicists came here, and then a couple more came, and now there's a big, mass of people here. And it ended up being mostly focused on neutrino physics. So there's a center for neutrino physics here at Virginia Tech, which I guess goes back to some strategic decision that the department made sometime in the 90s. Then I think most of the community was shifting towards collider physics in the run up to the Large Hadron Collider. And Virginia Tech, being a somewhat smaller department, didn't think they could compete, I guess, in the collider physics arena. So they had to make the strategic choice to really focus on neutrino physics, but they thought they could make a difference. And I think that's sort of paying off. I mean, now a lot of the community is shifting towards neutrino physics.
So what is the significance of competing?
Of competing?
Yeah, you said they wouldn't be able to compete. Is it basically like there's another institution that's already more well-funded and has more people and is able to do?
Yeah, that's right. I mean, I think a lot of times, people have different ideas of what a physics firm should be. Some people think maybe you should cover all possible bases, have someone doing condensed matter theory, someone doing condensed matter experiments, someone doing plasma physics, someone doing, all possible types of particle physics and so on. But then maybe you don't have any one area that's all that great, So that's one direction. That's fine. I mean, there's a good argument, I think, for going in that direction anyway. But other people think maybe it's better to have some really core focus, and then, maybe then you take advantage of synergies, people working on complementary things in similar areas. So
yeah,
and a lot of departments go that route.
So looking at your website, I see that you've lived in 6 different places in the last 10 years or so. Have those moves been motivated entirely by your career in physics?
Yeah, I mean, probably like most humans, it's a little bit of partially professional and partially family, related.
Yeah.
But yeah, certainly the professional parts played a big role. I mean, the short reason why, in this field, most people move around a lot, especially when you're pretty young, is that finding permanent positions is challenging.
Mm-hmm.
It's very competitive. There just are far more interested people than there are spots for them to occupy for permanent positions. So it leads to people doing short-term positions, which are called postdocs. So after you get your PhD, you go do research somewhere for 2 to 5 years. It's usually 2 to 3. Sometimes there are longer ones, and basically just delay the decision of whether or not to give up. Because it is very competitive. I mean, a lot of people, the statistics are that it's a challenging jump to make, to go from non-permanent position to something tenure track.
Yeah, so it looks like you did a postdoc in Los Alamos, New Mexico, another one in Denmark, and another one in Penn State. Now I see, most recently you lived in South Dakota and now Virginia Tech, where your rank is junior. What does that differentiate? How does that differentiated from a postdoc?
Oh, so it just means, postdoc is guaranteed to not be permanent. There's almost always some fixed term to it. It's like, typically it'll be like 2 years, maybe 3 years for good behavior. If you're really doing well, maybe you can get extended for 1 year, something like that. Whereas now a junior position means junior faculty, meaning tenured track, but not tenured. So tenured then is senior.
Right. So tenured track meaning maybe it's going to work out and you're going to be tenured someday.
Yeah. Like at least that's the path.
Okay. So what happened in South Dakota?
So I wanted to leave. Yeah.
Because of the allure of the neutrinos of Virginia, or?
Yeah, but for a combination of professional and family reasons. I mean, I like very much the nature aspect of Blacksburg, Virginia. It's just a really pretty area. It's very green and mountainous, and that is a non-negligible factor for me. And then, the physics is like remarkably different. I mean, it's a much, much bigger department. And a big thing that was unusual for me being in South Dakota is I was the only theoretical physicist. Everyone else was an experimentalist. So I had never been in a situation like that before. And they were fine people. There's nothing, they were great. But theorists and experimentalists are very different. And it's just nice being around other people who are theorists, but also other people who are doing pretty similar things to what I'm doing.
Yeah. So can we talk a little bit about that distinction?
Right. Sure. Yeah. So I don't know how common this is in other sciences and other branches of science, but in physics, for whatever reason, experiment and theory have become sufficiently complex and technical that there are very few people who do both. They really are, things that at the PhD level, you're already deciding, which one you're going to go into.
Mm-hmm. And what's the difference?
Yeah, the difference, well, I guess the difference is, experimentalists actually physically make an experiment and conduct the analysis, and they build stuff. They build things with their hands most of the time. Whereas theorists don't. We build things with math. We build things with computers and, with models. So that's the big difference.
Mm-hmm.
Yeah, but it's not like, it's definitely not the case that one is more important than the other in my mind. To advance in science, we absolutely need both. And really what I'm interested in is the interplay between the two. So sometimes what people describe my direction is called phenomenology. Mm-hmm. Meaning I'm a theorist, but a theorist very, very concerned with experimental data. Like, if it's a theory that has no hope of being tested in my lifetime, then I don't care. I'm not going to work on that because that's irrelevant for me, or maybe probably even my grandchildren. So I want to do things, ideally, that are even more short-term than that really can be tested in the next few years.
So how did you find yourself going in that direction rather than in the experimental direction?
To be honest, right? I mean, it really, to be honest, it was like a very definitive moment in my life when I had some vague idea of like who this guy Einstein was, but somehow, very luckily, when I was 16, some family friend gave me a copy of A Brief History of Time, this book by Stephen Hawking. And like, I didn't know anything about physics, let alone theoretical physics, but it was very exciting. Like, I didn't know, somehow, at the one hand, I didn't think a lot of the questions even had scientific answers or that you could approach in a scientific way. Like, how does the universe start? And where is the universe going? How is it going to end? And then on the other hand, there were questions that I thought somehow that we already knew the answer to, like, what is matter? What is stuff? And like, what? How do we not know the answer to that? So that was very exciting to realize that there was, because like when you're first learning about science, or at least for me, a lot of times there was like this tendency of like, oh God, it would have been so exciting to live 100 years ago. There were so many things to be discovered. But we're in a moment like that, right? Where there's so much stuff that we don't understand that's there. It's just sitting in front of us. We don't quite get all of it.
Yeah.
So to me, that's a super exciting part of this pursuit.
Yeah. So, okay, speaking of things that are right there and we don't know what the hell's going on,
Yeah,
let's talk about dark matter.
right.
So, dark matter is something that is affected by gravity, but we can't see it and we can't touch it.
Right. And hopefully, one of those things you said, one of those caveats, the things that we can't do with it, hopefully those caveats are actually wrong caveats, and that we can actually touch it at least a little bit, or we can actually see it at least a little bit.
Yeah.
Because otherwise we're going to be stuck in the dark for a very long time. But it's right. The main thing to emphasize with dark matter is that we call it dark because so far it doesn't interact with the electromagnetic spectrum at all, whether it's visible light or radio or gamma rays, nothing as far as we could tell. So in that sense, it's dark. But there's also matter because it interacts with gravity just like ordinary matter does. And that's the only way we really know it exists, is because it tugs on visible objects.
Yeah. So when I look around online, I see that the way that we know that it exists is because distant galaxies or systems are spinning in a way that is perhaps faster than we would expect them to spin based on the observable matter within that system. So it sounds like that's like the predominant way that these kinds of measurements are made. But is there actual dark matter present in a more local sense? Like,
Yes. I mean,
is
like,
it right here among us? Is it at the core of the Earth? Is it?
yeah. So, yes, there is dark matter among us right now that seems not to be doing very much. So that's basically how we know these things. Like, it's, you can't touch it. You can't reach out and grab it in the same way we can grab ordinary matter. But we hope, right, that that's not exactly true. We hope that there are just feeble interactions between ordinary matter like us and whatever this dark matter stuff is. And there are a lot of experiments around the world looking for that effect, looking for basically dark matter bumping into ordinary matter. So in the grand scheme of things, we want to talk about ways of detecting dark matter. There are three main ways that people go about doing this. This is sort of, this basically covers, I think, all possible ways of detecting dark matter, which are to either make it, break it, or wait for it. So making it is you can actually produce it in a collider. So you could go to like this place, the Large Hadron Collider, that slams together protons and other hadrons. And because of this cool thing called E equals mc squared, you can convert energy into mass. So, like the Higgs boson is this really heavy particle that's 100 times more massive than a proton, but we can make it at the Large Hadron Collider because those protons that they're colliding have so much energy that they can produce this new particle. So maybe we can do that with dark matter. We don't know. If we did do that at the Large Hadron Collider, what would happen is, right, we would have some collision take place, and we would look at the particles coming out of the collision, and there would be some imbalance of energy and momentum. So basically, right, you can imagine like two billiard balls colliding, and then, the collision point we don't actually see. We just see then, finally, ordinarily we'd see the two billiard balls come out, but in the case of making dark matter, you'd see maybe just one coming out. And it looks like the visible thing that you see is recoiling against nothing. So that would be a clear signature of producing something like dark matter. That hasn't been seen, unfortunately. So you can also break dark matter. So that was the making it route. You can also break it because you could look at regions of, say, our galaxy or other regions of the universe that have a lot of dark matter. So we expect there to be a lot of dark matter in the center of the galaxy because of gravity. Gravity wants everything to sit towards the center. And so dark matter can start bumping into itself. And depending on the nature of dark matter, it could could produce new visible particles that we can go and look for with telescopes.
Mm-hmm.
And then the final route, going back to what we were talking about, if we want to touch dark matter, this is called the wait for it route, or what people call direct detection. So these are typically deep underground experiments like the super CDMS detector or the xenon 1-ton detector. These are just experiments basically where they take a big mass of ordinary matter, something that can be instrumented and understood pretty well, and you bury it underground because you want to get rid of boring radioactive backgrounds and surface activity, things from cosmic rays bombarding the Earth. And then you just wait for a long time and see if you see your ordinary matter act funny, like get bumped by some invisible thing knocking into it. So yeah, those are the three main routes.
And so have any of those worked in any way?
They have not. Well, okay, so they've all worked spectacularly in not finding dark matter. You know, so it's not that this doesn't give us information, right? It just tells us increasingly more stringent facts about dark matter, right? So maybe I like the idea that dark matter actually isn't dark. Maybe it just has a really, really tiny electric charge. Right. You know, compared to the electron, which is the ordinary thing we think of as carrying electric charge, maybe dark matter just feels like a trillionth or something of the electron charge. If that's the case, I can still scatter in direct detection experiments and go and look for this dark matter bumping into my nucleus in the detector. And so, yeah, it still gives us information like that. It still improves, you know, the upper bound on how much charge dark matter can carry, for example.
Yeah. So you mentioned earlier that dark matter doesn't interact with, or it's not, I'm not going to be able to articulate this the same way you said it, but electromagnetically,
right?
There's no sort of light produced by it.
Yeah.
Could that potentially just be that it's off the scale? Is that kind of what you're getting at in terms of talking about the electrical charge, that it's just beyond the boundaries of what we're able to measure?
Yeah. So it would be basically just that, that's basically why those direct detection experiments need to be so big. So a way of thinking about, you know, let me imagine a really simplified experiment of this type where I just have some cube of detector mass, and say in my cube, I can always tell if some particle that's coming through bumps into someone in my cube, okay? So the way that particle physicists have of sort of describing this scenario is, you know, one thing that controls how many scattering events I have is the size of my cube, right? If I had a bigger cube, I'd have more scattering events. But the other crucial thing is how do I interact? And people call this a cross-section. You can think of it, again, going back to billiard balls, you could think of it in a classical physics sense of like, how big is this particle coming in? How much cross-sectional area does it present to my detector? So if that's bigger, I'll have a bigger probability, I'll have more scattering events. But the problem is we don't know what the cross-section for dark matter is. We don't know what its probability is of interacting with stuff. So we make bigger and bigger detectors, and also more and more sensitive detectors. So depending on exactly where the dark matter mass ends up lying, basically what's the mass of that particle that is dark matter, you know, one direction is just make bigger experiments. Another is look for even more feeble signals, even smaller energy depositions. And this basically probes lighter dark matter masses.
Yeah, so I heard about something in Canada called it was called SNOW. Some kind of underground, something like what you described. There's a deep tunnel down into the ground. There's a vessel of water down at the bottom.
Right. To shield, basically.
To shield?
Well, so most of the time, one of the reasons why these are always buried is that there is too much activity at the surface of the Earth, because the Earth is getting bombarded by cosmic rays. These are basically high energy protons and other nuclei. And those make a spray of other particles that are very annoying when you're trying to do sensitive experiments, you know? So that's like ordinary particles that, you know, as a fundamental particle theorist, I don't really care about because we already discovered those particles a long time ago. So that's why they're annoying. You want to basically just bury your detector and also maybe put shielding like this water to block out ordinary boring stuff from the surface.
Yeah.
And then you look for this very, very, very rare interaction.
Boring, get it?
Yeah. Well, boring is the ordinary stuff at the surface.
No, I meant like digging, boring.
Oh, yeah.
So does that mean that using outer space as a medium or an area for conducting these kind of tests is basically off limits in the sense that there's too much other activity?
So for exactly that type, kind of, it means, yeah, that space isn't great. I mean, space is good for two reasons, though, for other types of dark matter searches. So if you want to go look for the dark matter that's breaking itself, for example, that's annihilating, say in the galactic center, then you do want to be, it's helpful to be up in space, some satellite, and you can observe interesting photon signals or electrons coming from dark matter annihilation that you can sample with your satellite detector in space. So that's one way. Another way that people are thinking more about is, because we've eliminated a lot of possibilities for dark matter, we have to start being maybe creative and re-examining the assumptions that went into all of these very stringent limits we have on dark matter. And one important one is maybe actually dark matter interacts somewhat strongly, much more strongly than we would naively think from all of these experiments saying dark matter doesn't interact with us. And one way it could be hiding, if it's at fairly low mass, because low mass means even if I have a pretty big cross section, like I have the analogy with billiard balls doesn't quite work because you always think of bigger billiard balls having larger mass. But in this case, what I'm talking about is a dark matter particle that's light in terms of its mass, but has a big probability to interact with the detector. And that is a hard thing to see in a lot of experiments right now, in part because they are buried underground. So that's where non-trivial experiments, either at the surface or even using rockets or balloons, may be able to play a role. So, and that's very new and speculative, but that's an interesting direction that other people are pursuing and I'm thinking about too. Oh, so everything is muted.
That's me muted. You
Okay.
are not muted. Okay, we're good. So rockets and balloons. Are you working with other people at Virginia, what is it, Virginia Tech, who are conducting these experiments, and then you're analyzing the data from the
No. So the rockets and balloon part is really new. So I still am like working on baseline theoretical estimates for, how much dark matter you expect to see. Basically, how many events do you expect to see with these type of experiments? So yeah, that part, like I said, is very, very preliminary and very new. But that's actually, I think those are directions that people like me, who are what I said as a phenomenologist, someone who's a theorist but interested in experiments. Something I think we need to think more about is thinking about, on the one hand, using existing experimental data in new ways. We have like an amazing suite of experiments around the world, and oftentimes it's just a little tweak of a data analysis or a little tweak of some experimental setup that will allow you to use the same experiment to probe a totally different type of interaction or particle. And then another thing is basically having sort of low cost new experiments, like some small rocket or small balloon experiment. That's something I didn't emphasize, but like basically it seems like those types of experiments looking for this light dark matter that is fairly strongly interacting, those experiments would not need to be big at all. I mean, the competitor experiments that I'm talking about, these underground buried experiments, are literally 1 ton now, whereas these rocket experiments, the detector itself would have to be like a few grams. So it would be wildly different.
So in imagining like deploying one of these balloon rocket type things, what kind of budget are we talking about?
It would
Roughly?
still be in millions. It would be in millions, but not tens or anything above that. It would be in the $1 million range probably. But that's also, by the way, like huge error bars when I say anything having to do with dollars, because
yeah, sure. Just trying to get a rough sense. So like $100, $1,000.
You remember that, right? The big difference between theorists and experimentalists is theorists like equations and models, and experimentalists like equipment and building things with their hands. And so I'm not building the rocket. So really, I don't know how expensive such things are going to be. But
Yeah.
based on some simplistic estimates, it's something like that. Yeah.
Okay. So you mentioned something about maybe somebody already did a similar experiment and you can reuse that experiment for different purposes.
Right.
I want to ask about that. So what is the state of kind of collaboration between physicists around the world? Like, it seems like you could almost, I mean, there could almost be a niche for someone who actually doesn't do any theory or any experiments at all and is really just kind of like a
Oh,
librarian of physics activity who just seeks to like connect physicists with each other who are doing similar work and may not have to reinvent the wheel all the time. Is
maybe.
that something
Maybe.
you find in your work, or like how do you know that you're not wasting your time?
You mean what in terms of doing something someone else has already done,
Yes.
or well, I guess because that's always basically step one when you have a cool, exciting idea is make sure it's not just your own ignorance, that it hasn't already been done. So you have to
How do
do
you how do you
literature,
find that out?
yeah, literature searches.
So
Yeah,
you search on arxiv.org or
yeah,
whatever it
the
is?
archive. Yeah, that's right. Yeah,
Is that
which
the primary source for all physicians in the world or
yeah,
physicists in the
yeah.
world?
I mean, I think so. That and Inspire, which is this database that searches not only the archive but also physics journals, especially pre-archive papers. Because the archive really started getting used in the early to mid '90s. Which, right, by the way, that's an interesting development in physics. That it started out as what's called a preprint server. So it started out at Los Alamos, by the way. So people started using it just as a repository for posting their papers that were basically done but hadn't been peer reviewed. And that was helpful because, it basically just sped up communication. So then you get to know the main results of a paper before it's even been peer reviewed and appears in a journal, which can take months. And, sometimes many months. So that
Yeah.
really set things up, and in some cases, in some people's minds, have eliminated the need for publishing at all because it's totally open. Anyone in the world can access the archive, and once scientists get to know your results and start using it, maybe that's good enough. Some people have that attitude.
Do you?
In a lot of ways, no. I mean, I, I still think the default should be to try to get something published in a journal. I mean, I think typically papers are improved even if the fundamental results are not changed. Um, Having an outside, independent, and typically anonymous referee is a good idea.
Hmm.
So I don't dislike that. I do. I mean, the main thing I think the archive has going for it, though, is just having total open access. There's no closed doors. Anyone in the world can go look up a paper.
So when you refer to the archive, you're talking about arxiv.org?
Yes, that's right.
Okay, just to clarify. Okay, and then
Which
this
is called,
Inspire,
yeah,
okay, everyone just refers to it as the archive.
yeah,
Okay,
yeah.
distinct from the Internet Archive.
Right. No one refers to the Internet Archive in our field, at least.
In my field, they do.
Right.
Okay, inspirehep.net.
Yeah,
That's,
that's a database that grabs information not just from the archive but also from the Physical Review and the Journal of High Energy Particle Physics, Journal of Cosmology and Astroparticle Physics, and a million other journals. That's just basically the go-to searchable database for all physics papers.
mhm. So is that those two sites that's kind of the state of the art? Are there derivative projects that are making attempts to make the information more accessible or discoverable in these
Not
archives?
as far as I know. No.
Okay. Gosh, that seems like such an important thing to work on. Like,
So what do you have in mind?
I don't know. I just find that so in my work, I'm a software developer. I work
Yeah.
at GitHub, and so many people are reinventing the wheel all the time. There's already an existing solution to a problem, and people like to be creative. They like to solve problems, and in many cases, they like to start from scratch. in
Mhm.
solving these problems when in many cases it could be more practical to just apply an existing tool to the problem.
Right. Right.
And I feel like this is not unique to the world of software development. It's like
Yeah, sure.
there's billions of people in the world and a lot of people are working on the same problems, and if it was easier for people to discover whether or not somebody was already working on the same thing, we
Mhm.
could save ourselves a lot of
Yeah.
time and energy, and we could collaborate better.
Right. Right. Yeah, that's true. There is so I don't know how much this is being used in physics. Seems like it hasn't been used as much, but I know that there are certain developments towards what people call open science, which I think are very interesting. And I don't think has really been done very much in physics, but basically where to differing degrees you even have sort of like an open notebook policy where all active research is publicly available. You know,
Yeah.
uh, that's interesting, and I think there is an interesting argument for that, and it would totally change collaboration and the way science is done, and also even maybe credit, right? Because
Yeah.
if everyone, if you make it totally open, potentially lots of people you don't even intend to could end up contributing, which is interesting. There are pros and cons there probably.
So are you saying that the typical flow now today is that
Yeah.
that work is published after a process is entirely completed and it's kind of like a closed book at that point? Are you talking about open science being more of a let's open up the conversation from the beginning of the
Yeah,
project, or?
yeah, yeah. So open science, in my understanding, is sort of the most radical alternative to old school journals, where that's the only thing that exists is the journal version. The archive is sort of in between those two extremes, I think. I mean, the archive, because people um, can almost infinitely, I don't know, there may be some upper bound, but you can keep editing the journal, your paper on the archive. Some people edit papers many years after the fact, especially if it's a big like review article or something. Like I want to write a paper summarizing everything about dark matter. Well, I'm going to have to update that thing, right? Because it's an active field. So there are papers like that where, it's certainly not like an old school journal, right? Where I have to like dust off the old thing and start all over again or something and republish a whole other version. I could
Yeah.
just do it on the archive, right? I don't have to ask permission for anyone. That's great. But then open science is going one step even further, which is like, this is what I'm doing now. It's not even published. This is what I'm thinking about. I mean, that sounds more along the lines of what you had in mind. What you were saying is to basically stop from reinventing the wheel,
Yeah.
right?
Yeah.
Yeah.
Or
So
to have somebody notice that you're doing something wrong and jump in before you waste
right.
your time.
It does end up wasting a lot of time, that element of it, especially in my field, especially when there's an anomaly. So that when anomalies crop up in theoretical particle physics, it's a very interesting time. Um, so because that's what everyone wants. Because we know that we know our understanding of the universe is wrong on some level. We have this thing called the standard model of particle physics, how quarks and electrons and their cousins, how all of those particles interact. And they don't describe dark matter, and they don't describe why neutrinos have mass, even though data dictates that neutrinos do have mass. So there are known things that the standard model doesn't explain. So anytime we have some new piece of data that might be a clue about what the correct theory is, there's a flurry of activity. And a lot of it is, like you said, reinventing the wheel, because you had your great idea to explain this new data, 1,000 other people did too, So there is a lot of wasted time.
Yeah.
Things like that.
So do you find that in those situations, like this brings to mind, like, Edison as the father of the light bulb when,
Right.
20 other people invented the light bulb at the same time, and
Yeah.
one person who, had the right access or, connections was
Yeah.
able to be credited as the person who actually discovered it. Does this still happen today in physics? Is it like?
Yes.
Yeah.
Yeah. Yeah. I mean, things like this came up with the Nobel Prize for the Higgs discovery. So that was, I think, now I forget exactly when that Nobel Prize was awarded. It was not that long after the discovery. But so, this particle that was theorized for many years finally was discovered by the Large Hadron Collider. And also, besides the fact that it was 1,000 experimentalists who actually made the discovery, none of which got the Nobel Prize, there were also many theorists who contributed to the understanding of the Higgs boson in the early days, and who equally well could have been argued to get credit for it. One of which who had already won a Nobel Prize for something else. He was not credited for the discovery of the Higgs with the Nobel again. But anyway, so yeah, there are always these issues.
Yeah. So this is really common in my line of work too, that, there are thousands of people involved in a project, and ultimately a handful of individuals who get credit or, publicly acknowledged for the work. There's actually, so GitHub has a new CEO who is pretty cool, and just gave a sort of introduction at a recent conference, wherein they celebrated the new image of the black hole that was created by the Event Horizon Telescope.
Yeah.
And they talked about all of the software that was used to produce that image. And it's like this cascading tree of all of these dependencies of software. So it's not just the one tool, it's a tool that depends on multiple tools that all depend on other tools. And there happened to be a number of people in the audience at this event who had actually been participants in authoring the software, the constituent pieces of software that were used to make this image. And so for them, it was like this great moment where in some cases they didn't even know that their work was being applied to this problem.
Oh, yeah.
And it was really gratifying for them. But so I'm really stoked about working at a place where we are, making an effort to acknowledge that there aren't like heroes who are solely responsible for these accomplishments and these discoveries.
Mm-hmm. Right. Exactly.
But it sounds like this is like, a pervasive issue that
it is very pervasive, but yeah, I mean, I think science definitely, and physics in particular, probably needs to do that more, give broader credit, and potentially, I don't know, that also probably makes science and physics a friendlier place too. Just acknowledging all of the different people and not just pretending like there was, like you said, one hero at the top or something who had the brilliant insight or something.
Yeah. So speaking of that, so in this summer at GitHub, we had a number of interns come in, and this is like now an annual thing where we have like a group of interns who come in, and they're usually younger people and just coming out of college, and they do really incredible work. Like they're not just like the new people who are, we're gonna like show them the ropes or whatever. It's often like the reverse. Like they actually know all these, they're the new kids and they're smarter than we are. Is that common in your field? Like, do you find that you're, working at the university with kids who are, or younger people who are like changing your notions of reality and the work that you're doing? Or is it often more like you've got to really kind of steep yourself in this for a really long time, and it isn't until you're in your 30s, 40s, 50s that you actually start to make really significant discoveries?
No, I think it's some combination of those extremes. I mean, I have definitely, since I moved here to Virginia Tech, I've found a lot of undergraduates who are really excited about research. And it's not super typical for undergraduates to be really do theoretical particle physics research because of like the technical aspect, because there is a lot of math background as well as physics background and blah, blah, blah. But, at the end of the day, most of the time we're talking about things bumping into other things, which is not very complicated. So, I'm super open to it. I mean, this summer, like I led a project with 3 other undergrads, which was really fun. And I definitely find that, yeah, maybe they don't know how to do some integral or whatever, some math stuff and other technical things, but they don't have the same sort of baggage, the same sort of biases that other people, once you've studied something 1,000 times, inevitably there are some biases and some blinders you have on.
Yes.
Just opening it up a little bit to, working with undergrads, for example, I found it super fun.
Yeah, that's great.
Yeah, they definitely always like, I'll have crazy questions that I never thought of and that are like wrong, and then also crazy questions that are really exciting and, you know, new directions.
Yeah.
So it's really fun.
Cool. I want to change the subject for a second. I want to ask this question. I'm thinking about visualizing dark matter. And
Yeah,
so
I have an answer.
you already have an answer?
Yeah, if you wanna, but you can. What was your?
Well, I guess what I'm wondering is like, if it, in our observations of its gravitational influence, do we
Right.
observe that it tends to take on the same shape as the physical matter that we know? Like, do we see
Yeah, it doesn't.
systems with like like planets or bodies that are orbiting each other that are composed of dark matter, or is it more like this nebulous sort of floating material that is not really? I mean, if it's affected by gravity, I would think that there would still be like you know two balls going
Yeah,
around each other.
yeah, yeah. So it ends up being much more diffuse than ordinary matter. It's much more puffy and spread out. So, for example, like just taking the Milky Way, you know, visibly is this cool thing with a disk and spiral arms. And if you look at it like edge on, it's basically this really thin disk and a big spherical bulge in the center. And dark matter, on the other hand, is basically a big sphere encompassing the whole thing that extends out even beyond the visible disk of the Milky Way.
So why then, if it's affected by gravity, then why hasn't it just, become a black hole or whatever? Why hasn't it converged upon itself or
Right.
accumulated into higher density?
Yeah, so basically for structure to start forming for things like solar systems and stars and all of that, and the spiral arms that we see in the visible Milky Way, for all that to start forming, you need things like dissipation and basically you need extra interactions. Gravity alone is not enough for everything. For the atoms, that basically form the Milky Way to start collapsing into a disk and forming this structure with stars, they have to have some way of losing energy and losing angular momentum, which is built in with electromagnetism, which is cool. But it doesn't seem like we have that for dark matter. One of the best ways, by the way, I thought you were going to ask me this originally, but I want to mention something about I think the best way to visualize dark matter, and also the best way for understanding why dark matter has to exist. So, right, you mentioned, one of the canonical ways people talk about, one of the earliest things was looking at basically stars in a galaxy. So Vera Rubin, for example, was famous for this observation, looking at, stars basically just look like they're going too fast. I can look at how much mass I have in a galaxy, and that tells me what the force is on these stars that are orbiting. And based on that mass, the stars are just going too fast. So I say I have to have something like dark matter, right? So an obvious alternative hypothesis would be maybe our understanding of gravity is wrong, right? For me
Right.
to make the inference that the stars are moving too fast, I have to say I really believe my theory of gravity, right, to make that inference.
Yeah.
So at that level, if you're just looking at basically like star motion data, it's hard to distinguish. Is it that gravity is wrong, or is it that I need dark matter? But one observation that really made a big difference in changing people's minds that we really need something like dark matter is what's called the bullet cluster.
Mm-hmm.
So can I show you an image?
Yep.
Let me.
Is this the work of Vera Rubin that you're mentioning?
Oh, this is the work. This is more modern, and this is actually a good example of what we were talking about earlier, because it was 3 totally different observations put together by, each one of these observations was a couple hundred people, if not a couple thousand people, and 3 different collaborations put together to make this image.
Yeah.
So a good example of there's no one genius behind this thing. Let's see. Well, why can I not just? If I was an experimentalist, you would be able to. Okay. Let me share Google Chrome, I guess. Can you see that or no?
Yeah, I see it.
Okay, so this is an interesting image. So right, there are three different things put on top of each other here.
Mm-hmm.
So the first is this sort of normal-ish looking space background, which is, you know, black with a bunch of white and yellow blobs, right?
Yeah.
So that's a Hubble image. So that's in visible wavelengths. And each of the blobs are galaxies. So that's why they're kind of fuzzy looking things. It's not like one star or something. It's like, you know, tons of stars in each of those blobs.
Yeah.
And you can sort of visibly tell there's one kind of cluster of galaxies on the left and one other cluster on the right.
Yeah.
Do you see my cursor, by the way?
I do. Yeah.
Okay, cool. Then the other important thing to know about clusters of galaxies is that most of the mass in clusters of galaxies is not in those individual galaxies, but in this interstellar gas. And the gas is so hot, it gets heated up by all the, because there's such strong gravity there, and the thing is so dense, and it gets so hot that you start emitting X-rays. And that's what's seen in this pink. So this is actually an image from an X-ray satellite. I think it's the Chandra X-ray telescope. So that's what's seen in red. And that's also why it's called the bullet cluster, because you can see some interesting shock formation in the pink.
Mm-hmm.
And then the final part is what's in the blue. And the blue is done through modeling. So a cool effect that is used routinely now in astronomy is what's called gravitational lensing. So you can use the fact that light gets bent around massive objects. You can use that to tell where a lot of mass is. So there's background light behind this cluster, and you can use a computer to look at how light gets bent. You know, the deflections are very tiny, and you really do need to use software to do this. There are some extreme examples where you can see it visibly. It really looks like someone just put like a clear lens on top of the image you're looking at. But this is a more subtle example. You have to use a computer to do it. And when a computer does that analysis, it seems that gravity is strongest in this blue region, which is visibly separated from the pink.
Mm-hmm.
And the important thing is that the pink is where we think by far the dominant amount of ordinary matter is. So this is the cool thing, right? So going back to like the olden days when we first started looking at how stars move in galaxies and so on, that was great. But the problem is that that's a system where dark matter and visible matter are just sitting on top of each other. But this was a natural system where these two clusters collided. They fell into each other because of their mutual gravity. Originally, they also had dark matter and ordinary matter on top of each other, the pink and the blue in this picture.
Yeah.
But then they collided, and the pink, which is ordinary stuff, hydrogen gas, that does all kinds of complicated stuff when it smacks into itself. You know, it forms a shock because you collide with other hydrogen atoms and so on. You know, it makes this complicated structure. But the blue seemed to just go right past it. And so nature did this really wonderful experiment for us to separate out dark matter from ordinary matter. And again, right, if I had the hypothesis that to explain fast-moving stars and galaxies, I could explain it just with modifying gravity, well, this observation contradicts that, because what if I really thought I could just get away with modifying gravity, I would expect the lensing to still be centered on where the pink is. I would expect the dominant source of gravity to still be where most of the ordinary matter is. It would just have a slightly different shape to it or something. You know, it'd be a stronger gravitational lensing signal. But that's definitively not the case based on that. So this
when was this sort of composite?
I think it was something like 2008 or 2009, something like that.
So relatively recently.
Yeah, and this was the first time this kind of cluster collision was found to occur. But now there are like dozens of these systems where the same sort of phenomena happen.
So in the time from 1930 to 2008, was there some state of like collective indecision about whether our model of gravity was wrong or whether we were really
Yeah.
right about dark matter?
Yes. Yes. And yes, there was a collective indecision. I think it started to become more favored, eventually, I don't know when exactly, maybe 80s or something, that dark matter was a more likely explanation. It was just sort of a simpler modification. Because at the end of the day, I'm saying Einstein's theory of gravity is wrong, and I have to cook up a whole other new theory of gravity, or I just have some new particle, you know. So I think that's why a lot of people thought, well, maybe it's just a new particle. That doesn't seem that hard or that big of a modification. Um, so, but with this sort of thing, yeah, maybe I don't know if you've encountered this in other fields too, but there are always going to be holdouts. There are always going to be people who love their new theory of gravity model that they've always worked on, and they're never going to stop working on it no matter what the data is. But observations like this make it very challenging, to say the least, for
Right.
models of that type.
Right.
Yeah.
Hey, can you stop the screen share so I can see you again?
Oh yeah.
You're very small in the corner over there. Hey, okay. Oh, also, okay, wait. So did you write those equations on the chalkboard specifically for this call?
No. I didn't erase any equations though.
Okay, so there's no
There's
intellectual property.
super boring. No, by the way, I don't have any intellectual property.
Okay.
Yeah.
Cool. What is on the board back there?
One thing, well, the most important thing you probably can't even see, which is just for students, which is a funny thing that we use, which I always put at the top because people always forget. We use a funny system of units where I measure everything in energy. If I want to talk about how big the universe is, I talk about it in inverse energy units, and talk about the mass of a particle in energy units, and so on. Everything's in energy. Area is in energy. Anyway, that's just a thing called natural units. So by the way, because it helps make things more physical. So like one of the only equation I mentioned so far, right, was E equals mc squared, the thing everyone knows.
Right.
But the physical content of that equation is made way more apparent by just saying the speed of light is 1. Let me forget about the speed of light. So what E equals mc squared is saying is E equals m. That's the physical content of that equation, which is profound and important, is that mass is a huge amount of energy. Mass is energy. They are, the same thing.
It's mass energy because it represents an accumulation of atoms that are all electrically charged particles?
No, it has nothing to do with the electric charge. Yeah. It's just, so like dark matter, for example, right? Dark matter we think may not have any electric charge, but it definitely has mass.
Yeah.
So it's a way of talking about the energy of a particle that resides with that particle even when it's not moving. So in other words, to create the thing itself, you require some energy.
Yeah, okay. So I'm remembering there was like this may be a little off base, but I remember a Richard Feynman conversation about a fire and how this tree grew, and the tree was the result of sunlight shining down on earth, and the combination of the water and sunlight and the air creating this sort of accumulation of carbon in the tree, and that's just like basically a stored energy that is then later this represented as this very chaotic fire where all the energy is coming back out.
Right, exactly.
Is that similar?
Exactly.
Or?
Yes, exactly. Right.
Okay.
So like what that equation means, that E equals mc squared, is, I can create mass if I have enough energy. So that's, for example, how the Large Hadron Collider created Higgs particles, right? it took protons, which are 100 GeV, which are 1 GeV, and it produced Higgs bosons, which are 100 GeV. It created a more massive particle out of slamming together lower mass particles, but with huge energies. And then the opposite can happen too. So I can also destroy mass and create a lot of energy. And that can happen if I take matter and antimatter and put them together. So if I take like an electron and an anti-electron, those guys both have mass.
What's an anti-electron? What's antimatter?
Yeah, so antimatter is not dark matter, is one important thing to say. But antimatter is a pretty amazing fact about the world, that every particle that we know of has an antipartner. And this was originally also sort of an amazing thing, is that this was predicted first. It was predicted by some crazy guy with a blackboard before it was experimentally observed, that there had to be antiparticles. There had to be, to make things consistent with quantum mechanics and special relativity, all particles had to have another partner who had exactly the same mass and all the same properties, except opposite electric charge. And so he said, well, okay, I know electrons exist, and then if I just put in these ingredients of quantum mechanics and special relativity, I have to have antimatter around. I have to have these anti-electrons. And then eventually they were found in cosmic ray experiments. And now we produce them too in accelerators.
So that's present in all, so all matter has its corollary antimatter that is
so there's
residing beside it or in orbit with it, or?
No. Okay, so right. So that's the most mysterious part of antimatter we don't understand still. We know on a fundamental level that all of the particles we know exist all have antipartners. In some cases, if they're neutral particles, then they can basically have their antipartner can be itself. But for whatever reason, there was something, this happened beyond the standard model. Again, a clue from where reality comes into contradiction with our basic model. The universe, atoms in our room and the galaxy as a whole, every galaxy we've ever seen, has a predominance of matter and not antimatter. Although the standard model of particle physics treats them almost the same. It doesn't treat them differently enough to explain why in the real world we see so much matter and not very much antimatter. There had to have been some interesting process in the early universe that happened that produced a preponderance of matter over antimatter.
But you said that all matter has its.
Yeah. So what I mean is, someone tells you what's the inventory of the universe, right? What are all the particles we've ever seen? They all have antipartners. Not in the same abundances, though.
Well, if they all have antipartners, then
all that I mean is, okay, so right, there are a gazillion electrons, right, in the universe, however many it is. But I know for sure that electrons have antipartners. We have found them in the lab, and they definitively exist. The problem that I'm trying to explain, that we don't understand, that we would like to understand, is why are there a gazillion electrons and no anti-electrons in the real world? We know that there are some anti-electrons. They for sure exist, and we know how to make them in the lab.
Yeah.
Whatever made this preponderance of electrons over anti-electrons, that's beyond our theory right now.
Yeah. I don't understand what you're talking about.
So because I say that there has to be an anti-partner?
Yeah, if there has to be one. And you're saying, but then you're saying that there's an imbalance, that there is more matter than antimatter.
Right.
If by nature all matter has its partner antimatter, then isn't it a 1-to-1 ratio?
Right. So it ends up being about history. So the way that the standard model treats things is that they're totally equivalent, or almost totally equivalent. And so there was some process in the early universe that violated some of the conditions that we have in the standard model that made a preponderance of matter over antimatter that we don't know the answer to.
Yeah.
But we have definitively found antipartners for every particle.
So it sounds like dark matter is only one of the things that sort of challenges the standard model?
Yeah, yeah. The three big things are, well, maybe four big things are dark matter, dark energy, neutrinos, which have mass but shouldn't have mass in the standard model.
Yeah.
Then what's called baryogenesis, which is this thing about why is there more matter than antimatter.
Yeah.
Those are four.
Variogenesis.
What?
Variogenesis, that's a good name.
Yeah, how do you make baryons, but
Right.
not baryons?
Okay, wait, I want to put a cap on that. We only have a little bit of time left, and I want to ask a few other
Yeah.
kind of unrelated questions. So, one is about, so I want to, you showed that image where, it was a composite image created by 3 different teams.
Mm-hmm.
What team had the sort of idea to bring these observations together to form like a composite observation? And secondarily, where did that data come from and how did they share it? So not in the sense of a PDF paper. I mean like raw observational data from like Hubble, for example.
Right. So I think, so I don't know the answer. I think that this came from the X-ray people though, which again, I think also was Chandra. There's a lot of stuff I don't know for sure the answer to, but I think it was the Chandra X-ray people who did this observation of the bullet cluster who, you want to take advantage of all the data you have of the system you're observing. And a good thing about data that's collected with NASA satellites is that I think it's required by law for most of that to be publicly available. So as far as I remember, it was mostly initiated by these Chandra people.
So NASA just has this gargantuan archive of data recorded by all of its like telescopes and.
I believe so. I don't typically need to use it, so that's why I'm not certain.
Yeah, I'm curious if like that's what how that works on an international scale and like across nations. Like, so China, for example, like are there lots of Chinese physicists? Do you collaborate with Chinese physicists, or is it like sort of?
So in my field especially, it's super international. And yeah, I've worked with people who I've never met, in various countries. Yeah, in China, in Iran. Iran is maybe the hardest country to actually try to interact with people because you can't really get them to come here. Yeah, I have a collaborator I've written a couple papers with in Iran, and I don't know if I'll ever meet her, unfortunately.
Yeah, actually, that's kind of a sad story because GitHub recently made some policy changes to conform to some sort of U.S. trade control law that required us to disable accounts for people living in embargoed countries, and I think Iran is one of those countries. So there were a bunch of people like GitHub users who were just like all of a sudden not able to access their accounts anymore.
Jeez, that sucks.
But it sounds like that was like a decision that we were unable to do anything about,
Yeah.
without being, going against the U.S. law.
Right.
Which sucks. But
yeah.
Okay, another thing I wanted to ask is just like what is your end goal with the work that you're doing? Like, is it satisfying enough to just have this kind of curiosity and like is it enough to be just constantly like seeking answers, or are you actually hoping that in your lifetime you're gonna some radical change is gonna come about because of some discovery?
I of course hope that there is a radical change. I mean, yes, that's the reason why basically, like I was saying, whenever there's an anomaly in physics, some new data crops up that seems like maybe this is the moment that everyone's been waiting for, right?
Yeah.
There's a flurry of activity because like that's what everyone's waiting for,
Yeah.
Very exciting.
So, sorry,
yeah.
Go ahead. Keep going.
Yeah. So I mean, it is enough for me. I don't have any rose-colored glasses on, thinking like we're for sure going to discover dark matter tomorrow, or even in my lifetime. We may not. But to me, it's so very exciting to be a part of this process, right? I mean, maybe some analogy is that, you know, we've stumbled into some room, a dark room, you know, we don't know what's in the room. We're fumbling around, working together, figuring out, like, is this a trap door, or is this your foot, or what are we doing? Where do we go? You know, so it's very exciting, but we don't know how big the room is. We don't know if it's a small house or a 50-room mansion or whatever, right? There's so many questions that are unknown right now.
Yeah.
So to me, that exploration is super exciting in and of itself, even if we, you know, don't actually find what 100% of dark matter is.
Right. Well, that's good.
Yeah.
As I was telling you, I had this neighbor, Bernard Sadoulet, who's like the head of the UC astrophysics department, and I was kind of asking him about the experiments that they've conducted and, you know, what they found, and he seemed a bit somber about it, right? Like, you know, he's nearing retirement. He's been working on this forever. And, you know, has a lot of accomplishments under his belt. I think he's been associated with 2 teams that have won Nobel Prizes. But I still got this feeling like he's kind of bummed out because they still haven't figured it out.
Right, right.
So I wonder, like, is that just something that's kind of baked into your experience of the work that you're doing? Is like, yes, it's a mystery and that appeals to me, but also we may not figure it out.
Right. Yeah. I mean, I think it's also maybe in the last couple of years there has been an important shift in particle physics because of the results of the Large Hadron Collider, especially, which were, in the end of the day, probably overhyped. I mean, this was a many decade-long process to construct the detector, and the Higgs discovery was supposed to be the first of many discoveries, because we were supposed to unlock a whole other symmetry of the universe, something called supersymmetry, which predicts yet other partners for all existing particles. And that theory has come up short, to say the least. There's no evidence for it at all in data. And that was really something that sort of the community almost as a whole bet on in terms of work and how they're devoting their time and resources. And so I think right now we're in a different state of affairs where we really recognize we are in many ways in this dark room, and, you know, there aren't really clear directions right now. Yeah. That's really the true description, I think, of how things are. It's not, you know, we have to keep pushing forward with the tools we have, you know, the existing experiments, and try to make the most of those. Like I was mentioning before, you know, reusing the same experiment with a slightly different analysis can oftentimes produce very interesting non-trivial results. And then also seeing what we can do to target well-motivated theories, ideally with low-cost experiments, because there are too many ideas of what this dark room that we're in can be from a theory.
Yeah. I just thought of another question. So I'm wondering what role artificial intelligence or machine learning might play in the advancement of our sort of analysis of this preponderance of like observational data.
Yeah. So I haven't been directly involved in anything along those lines, but I know, yeah, certainly parts of the community are getting more excited about that.
I'm wondering if like the existing observations that have already been made might contain a lot of really useful information.
Yeah, that's definitely possible.
Yeah.
I mean, again, I think that's totally along the lines of something I think we have to do as much as possible, right? Like we have to squeeze everything out of the data that we have.
Yeah.
That's ultimately how we're going to make progress. We're not going to make progress by guessing at the right theory and then, you know we have the right theory. We have too many good ideas right now.
Right.
Yeah. We have to have theory. We have to have an experiment come and kill some and hopefully find the right one.
Right.
Yeah.
Cool. Well, let's stop it there.
All right, great. Thanks, Zeke. It was
Thank
fun.
you for having me. I'm going to stop the recording.
Thank you for having me.
Yeah.